Hello YouTube, welcome back to my channel. My name is Tony and today we're going to cover dynamic programming intervals. In the previous videos, we already covered the minimax and knapsack problems, and in this video we will summarize 9 problems for intervals. Just like before, we're going to cover all the examples, we're going to cover all the solutions with a top-down approach. Interval type is on the easy side of among all the variation of dynamic programming. Now let's just go ahead and check some concrete example. First, balloon. So you are given n balloons and indexed from 0 to n-1. Each balloon is painted with a number and is represented by an array nums. And you are asked to burst all the balloons. If you burst the ith balloon, you will get the nums left times nums right and times nums I. And I is in the middle. And here's the left and right adjacent index of I. And after the burst, and the left and right become adjacent. This is very important condition. And return the maximum coins you can collect by bursting all the balloons wisely. So what's that mean? The question basically saying you have all the balloons right here, and each balloon is painted with a number, and the number represents a coin number. So basically, if you burst one particular balloon, you'll get a whole bunch of value. So what are the value you are getting? So let's check the first example. So let's say we have 3, 1, 5, 8. And if I burst 1 in this case, and I'll collect coins from 3 times 1 times 5, all the neighbors, the products of all the neighbors. And if I burst 5, I'll get 1 times 5 times 8. But 5 will be bursted, and 1 and 8 will be remained for the next round. You still can burst 8 and to collect the value from all the products from its neighbors. And let's check the examples was given by the solution. So 3, 1, 5, 8. If we burst 1, we will burst 1. 1 will be disappear in the next round, and within this round we'll get 3 times 1 times 5, and we have 3, 5, 8 left. And in this case, we're gonna burst 5, and once we burst 5, and we have 3 and 8 left, and that's in the next layer. And within this layer, we are gonna collect the value 3 times 5 and times 8, which is on the left hand side of 5 and on the right hand side of 5, and 3 times 5 times 8. And now we only have 3 and 8 left, and we're gonna burst 3. And be careful, in this case we're gonna times like 3 times the 8, and we're also gonna multiply by 1. And 1 is a virtual boundary, so which we have to manually add, otherwise the solution cannot be solved. Within the high level, we're going to solve this question by using top-down. That's in our mind. We are trying to break the large problem into a smaller problem. That's our thinking process. But within the machine, it's actually the opposite. So when we actually breaking down the bigger problem into smaller problem, and we hit the base case, just like the recursive function, and the recursive function return to the higher level, layer, and within the lower layer, which is the base case, which is actually a unit, like a smaller problem, and the smaller problem was being solved and aggregated to the bigger problem. That's how the stack works within recursion. So I know this is more like abstract. Once we see the code, you'll get more understanding. So let's think about how the machine works in this case to solve this problem. So we are given like 3, 1, 5, 8. So let's think about if we only have one particular coins right there. So for example, we have 3 right here. We only have one coin, which is 3, and the coins we can collect is 3 times 1 times 1, and then it's gonna be 3. And for example, if we only have one coin left, and in this case, we also hit base case, right? And we only have 1 times the virtual boundary 1, so 1 times 1 times 1 is also 1. And respectively for 5 and 8, we're going to get 5 and 8 because we only have that particular coin can be picked from. And the virtual boundary is always like 1 on the left hand side and right hand side. And we're going to collect either 5 and 8 respectively for the rest of the number. And that's for the cases that we only have one coin. But when we have actually 2 coins, and how do we do that? So actually we're gonna get the summation for 3 and 1. And why is that? Because you can either burst 3 first, or and you can either burst 1 first. Either case you're gonna get a 4. And same thing right here. If you have only 1 and 5 left, you're gonna get 6, and 5 and 8 you're gonna get 13. So from the smaller problem, we are building up to the bigger problem, and 3 and 1 will be solved, and then like we can move on to solve 3, 1, 5. we already solved 3 and 1, we already solved like a 1 and 5, and in this case we just take the maximum, right? So either 3 and 1, so we can either solve like 3 and 1 together and solve 1 separately, or we can solve 1 and 5 together and 3 separately, and we compare which one is bigger and we take the maximum value, and that's how the recursive function will approach. Actually, recursive function will be easier because it's more like a top down. So let's go over the example first. In this case, I used the Python trick to catch that. The reason is that the inner function looks like a recursive function. It's much easier to understand. So in the next slide, I'll manually cache that, so it's which is more like friendly to Java developer or C++ developer. Okay, so like we mentioned before, so we need two virtual boundaries, because on the left hand side or right hand side, if we want to burst 3 or 8, and we do not have 1 to multiply from. So you could do some special cases within the recursive function, but we don't like it. So special cases are always tough and also easy to make a mistake, and virtual boundary will solve the problem. So we don't have to care about the special cases anymore, or the corner cases. And now we have the recursive function right here, and the only two things we need for the recursive function is the left hand side the index and right hand side index, I and j. So we start I and j from the either very left and very right. So actually it's not here, it's actually here, because we have the virtual one right here and virtual one right here. So I will be under right here and j will be under the index next to 5 on the right hand side of 5. So that's the I and j, and that's why when we're looping through k, so we start from 2 to 5, because it's I plus 1 j minus 1, right? Okay, perfect. So with some understanding with the virtual boundary, let's go over the code. So let's come back to base case for later, and let's go over the recursive function first. From top-down thinking process, very simple, right? So we can burst either 2 or 3 or 1 or 4 and 5. So let's try out every single options we have. Let's burst 2, so which is I plus 1. I is right here, I plus 1 is 2, and I plus 2, I plus 3, all the way to here, all the way to here. And this is j minus 1. Remember, j is right here, the virtual boundary we just built. Okay, so we are going to burst every single one of them and trying out all the options we have, and which is the next line. So we're going to have the k is the number that we are looping through. So k is the number we are bursting. And this line is kind of confusing in the very beginning. And we are thinking, why are we supposed to times, for example, when we burst 1, right? Are we supposed to times 3 and 4 instead? So why did you times the boundary I and j? So the reason is that, so the recursive function has the priority. So when we actually calling the recursive function, so we're doing this. So we have I will times the left hand side right here and right hand side right here, because this guy will going back to the recursive function and will be calculated first, and this guy will be bursted first. So 2 and 3 will be gone, and 4 and 5 will be gone, and then the thing we left is on the right hand side or left hand side or right hand side, the virtual boundary, and those are the numbers being left, and 2 and 3 will be bursted, and 4 and 5 will also be bursted. So that's why those recursive function has the priority. Those will be gone first. So I all the way to k will be gone, and k all the way to j will be gone. And when those numbers are being gone, and we are left in with a virtual boundary 1 and 1 right here, that's why we will use the middle one, which is the k, times all the way to the left and times all the way to the right, because the recursive function has the priority. So just remember that. That's one of the tricks that getting confusing in the very beginning. But once we understand that, and we can get the entire idea of how the recursive function works, because we want to multiply all the way to the left and all the way to the right and burst everything in the middle. And same thing, we can burst this guy first, and then we can burst the rest of the solution. So this is the recursive function. If you don't have this header, and you have exponential time complexity, but we're going to reduce that to the n square. So how do we do that? Is it n square or n to the cube? I think it's n to the square. Okay, so let's go to the next slide and check how we manually cache that, and we're going to explain the cache as well. So this is the slide that I did manually cache, and we use hash map, and sometimes, like we mentioned in the previous video, we can use two-dimensional array, or in this case it's two-dimensional. It depends on your input, right? and to cache the value, and we're going to use ij, which represents the unique state. So why this is unique state? Because we start with ij. So in this case, we can burst, for example, 2 first, and we can burst 5 first, and then we can burst the rest of together. Or we can burst 5 first, and we can burst 2, and we are still left with the 314. But 314 will be solved by the stack. Okay, so 314 will be solved by stack if we burst 2 first and then burst 5, or burst 5 first and burst 2. So we're gonna solve this twice. So this is time consuming. We don't want to compute this multiple times. So instead, every time we reach the base case and we calculate the smaller cases, we want to cache the value, and that's how the cache works. So let's go over the code. We have the memo, which is the hash map. And we still have the virtual bound, we call it the recursive function. So whenever the value is being calculated, we just cache that. And how do we reach out to smaller cases? Just like we mentioned before, I is j here, right, j is right here. So for example, we burst 2 first, right? We burst 2 first, and then for example, we burst let's say 1 first. We burst 1 first, and then the recursive function will go from I all the way to k, which is right here. And then we are keep like breaking down, and in the second time we only have like 1, 2, 3, 1 left, and this is a bad example. Let's break down like this. Let's say we break 3 first. Let's say 2 first. I'm sorry. So let's burst 2 first, and we only have 2 left, and 2 is gonna reach base case because we only have I is right here and j is right here, and we only have this guy left, and we return 0, and the value we are adding up is actually 2. So this is the base case. So when I and j are equal in this case, so that's why we will cache the value. When I equal to 1 and j equal to 1, and we're gonna reach out to this case, and we're gonna solve this case. And same thing, like the smaller problem will be solved first. So whenever we solve in the bigger problem, all we have to do is calling back to the smaller function. So for example, when we trying to solve like 2 all the way to 1, and we're gonna calling back from the cache for 2 to 3 and 3 to 1, and then calling the base case for either 1 and 2. So that's how the recursive function works, and that's how the cache works, and this is gonna bring down the time complexity to the n square, and that's how we solve this, and we manually cache it. So the rest of the story will be identical to the previous explanation. I'm not gonna beat that horse. So let's move on to next slide. So 1039 minimum score for triangulation of polygon. So what the question basically say? Okay, let's read the question first. Given n, consider a convex n-sided polygon with the vertices labeled from a0 all the way to n-1, and in clockwise order. And suppose you triangulate a polygon into n-2 triangles, and for each triangle, the value of the triangle is the products of the labels of the vertices, and the total score of the triangulation is the sum of these values over n-2 triangles in triangulations. Return the smallest possible total score that you can achieve with the sum triangulations of the polygon. So what the question basically saying is, okay, so you have a whole bunch of numbers, and each number is the node for a triangle. For example, in this case, this is a bad example. This is actually the base case because we only have 3 numbers, and the 3 numbers can only form 1 triangle. So the number, the eventual value you'll get is 1 times 2 times 3, and this is the only triangle you can form because we only have 3 nodes. But when you have 4 nodes in the second example, 3, 7, 4, 5, so you can have 3 times 7 times 5 as your first triangle, or you can use split like this, and you can have 3 3 times 4 times 7. Okay, so something like that. So you can break like this, and you can break like this, and trying to get a the smallest possible total score. So if you think about this problem very carefully, right, and I think this problem is almost like identical to the burst balloon. So how is that? So the reason is that we're getting the products of the labels of the vertices. So how can we break down the 4 nodes into triangles? We actually only can pick node. How do we pick node? So we can either pick 7 as the node, or we can either pick the 4 as node. Is that correct? So let's say in the first cases, right? So if we pick 7 as the node, and then we can either have 3 times 7 times 4, and then 7 is gone, and then we can have 3 times 4 times 5. Okay, something like that. So if that's how we translate this particular problem into previous problem. So in the previous problem, we have burst some balloons and then reduce the adjacency, and in this cases we are picking the vertices as the node to form a triangle. So the way we can form a triangle is also with its neighbors. You cannot cross like the lines and with others to form a triangle. You can only form a triangle with your neighbors, and that's why you can pick 7 as your node. Let's read the question carefully. Let's go over the example one more time if you get confused. So let's say we pick 7 as the first triangle, right? So we can form a triangle with the 3, 7, 4. So 3, 7, 4, right? So this is the triangle we formed, and then we burst this node, and then we are left with the 3, 4, 5. So this is the guy we left. And if we pick 7 first, so we have 3, 7, 4. Oh, we already picked that. Okay, so let's go over this example, right? We pick 4 first, so we're gonna have 7, 4, 5, 7, 4, 5, and then we burst this guy, and then we left with the 3, 7, 5, 3, 7, 5. Okay, so this is actually how we translate it to the previous one, the burst balloon. And this question is medium. The reason is that it's even easier because in the previous problem, we have virtual boundaries. We have to manually add the virtual boundaries. And in this case, we are formed n-2 triangles. So we are told that we don't have the boundaries. We don't have the corners to deal with. We only have to form n-2 triangles. And so we can literally copy and paste the code into this problem with one caveat. So the previous one, we are looking for the maximum, so that's why we initialize the value as minimum. And in this case, we are looking for minimum, so that's why we're gonna initialize the previous results as the maximum value that we have, and then we eventually we are looking for the minimum value that we can get for total score. Okay, so we still have the memo, we still pass the ing as the index, and we still have the base case, and the base case in this case is a little bit different because we want to have a -2 triangles, and when we have less than 3 node, we cannot form a triangle, and that's why we have the corner cases right here. So j-1 plus 2, j-I plus 1 is less than 3. That means like we have less than 3 node and we cannot form a triangle, and that's the base case we have. And this is the standard, so when we have ing was being calculated, okay, perfect, so we just bring back from the cache, otherwise we just cache that. And if we already solved one particular smaller interval, so we just store that into the cache, and in case we're gonna call back later for the smaller problem. And that's the standard. And let's go over the recursive function. Still, like, we are trying to get the products of all the vertices, and that's why we have the ing, just like we explained before. And because we are bursting the middle one first, and we go bursting the middle one first, and that's why we get the left corner and the right corner, and times the one we bursted. So that's the value we are getting for the vertices. And so we are breaking down for the so for example right here, so we burst 4, and then we are still have 7. We have 7, 3 and 7 left, and on the right hand side we have 5 left. And that's how we breaking down the problem into smaller problem and trying to solve that by reusing recursive function. And then with the cache, we're going to bring down the time complexity to the n and to the square. So that's how we solve this question. So I'm not going to beat the dead horse because this problem is also identical to the previous one, burst balloon, so almost exactly like the same. And now let's go over the next problem, 375, guess the number higher or lower. And this is actually the second problem in the sequence, and there's another problem, guess number higher or lower 1, and that one's static. So we're given a number, for example the number is 1000, so you take a guess, and if you guess like so for example the particular number is 800, so you guess a 500, they will tell you, the API will tell you, oh, the number you're guessing is lower, so pick a higher number. You got 750. Obviously we are using binary search, and then eventually you reach out to 800 as your final result. And that's how the API helps you to determine the number you're higher or lower. And that one's easy because everything is static and there's no cost to pick. The cost for picking a number is 1, and for every single cases, so that's why you can use binary search. But in this case we are not. So let's read the question. We are playing the guessing game, and the game will work as follows. I pick a number between I and 1 and n, and you guess a number. If you guess the right number, you win the game. If you guess the wrong number, then I will tell you whether the number I picked is higher or lower. You'll continue the guessing every time you guess a wrong number, and you'll pay X dollar. If you guess a wrong number X, you pay X dollar. It's not 1 anymore, so that's why we cannot because the cost is bounded. It's tilted, right? So when you pick, for example, your first guess is like 50, and it will cost you 50. So instead, if I pick 1, so that'll be a different story because it only cost 1. So this is so different story than the first problem. And if you run out of memory, you lose the game. And given the particular n, return the minimum amount of the money you can. You need to guarantee a win regardless what number I pick. Okay, perfect. So how do we think about this problem? So we still this actually looks like a minimax a little bit, but we're still going to think about this problem in terms of the intervals, right? How do we think about it? Still, let's just think about the burst balloon cases, right? So we start with the smaller cases. So we have, for example, we have a number 1, we have number 2. We got no other choices. We can only pick that particular number, so that will be our cost. So when we have 2 numbers, we compare the cost and the smaller cost and stuff like that. So this is more like a building block from the smaller block to the bigger block. And that's also how we solve the problem. So when we have a whole bunch of numbers right here, so we can pick a middle one, or we can pick anyone. We can start with anyone, and then we can recursively solve that by breaking them into intervals. For example, the left and right intervals. So we're to go over the examples, so we'll have to check this. And let's check the solutions for this. In this case, we are using 2-dimensional array as cache. We still can use hash map, but if you're like C++ developer, should predefine array and will be helpful for optimize the speed, time complexity in terms of like solving this in the context. But if you're using Python, so it doesn't matter. I can tell a difference right here. Okay, so we're gonna use a cache, and we put the cache into the recursive function, and then we start doing this, right? And the base case will be when I is greater or equal to I, then we return 0. And because the cost will be determined in the recursive function, so we don't care. And in the cache value, if the cache was being already computed, so we just bring back from the cache. Otherwise, we just store after we calculated, we just store the value into the cache, and that's all standard. And we initialize the value as the infinite and as the biggest number, because we're not calculating the minimum number. So that's all standard. And now let's go over the recursive function. When we pick a number, the cost will be n, that particular number. If we pick x, and that number will be x, so this can be x, so you can rename this. So that's the cost. And then, so once we pick this number, we want to know, we want to recursively calculate the numbers on the left, and we want to recursively calculate the numbers on the right, and that's how we do it. So it's from I to nums minus I, because the num is already being picked. So I already picked this particular number, so go ahead and pick from the rest of the numbers. And same thing on the right hand side of the numbers, and that's another interval. So the interval eventually will hit the base case and return 0, and the cost will be accumulated in the recursive function. That's how we solve the problem. So now let's go over the next one. 516 longest palindrome subsequence. Given a string, find the longest palindromic subsequence of the length in S as a string. So you may assume the maximum length is like 1000. They're giving you a constraint, and this is more like a hint by saying that you can use n-square algorithms. And how do we solve that? And the way we are going to solve that is still by using breaking down into intervals, but I think this problem is much easier than previous one. So let's check. There are several conditions, right? So the first condition is we are trying to find the longest palindromic subsequence. So for subsequence, it's different with the subarray. With the subarray, you can go ahead by using like sliding window or other tricks, like you can pick a string from the middle, and you can spread from either side, left or right hand side, and to find the maximum substring or subarray. But in this case, substring, and we need to use dynamic programming, and we cannot start from middle, and we don't know like which one to pick, right? So we start from both sides. So B is right here, B is right here. So when you have two strings, within this string, if you have two characters are identical, that means you are gained two character. And in that case, you can shrink in both sides. So you can have I plus 1, j minus 1, because we can check something in the middle of trying to find out the more match like that. So in this case, we don't have this b anymore. We don't have this b anymore because we're gonna plus 2. We're gonna plus 2 in this round because we are already gained two character as the length of the subsequence. And if they are different, for example, in the middle, right, b, b, a, if they're in the middle and they're different, so b and a are different, so we either check on the left side or right side. How do we break it down in this case? So we're gonna check the bb or ba, right? bb, and because we know ba is not matching, so we're gonna try to find the second optimum by shrink one character. Either we cut the left character, it become ba, or we cut the right character, is bb. Okay, so with this logic in mind, so let's go over the example. The solution, we have the memo, everything's the same, standard. This is the base case. When we have I and j are matching, we only have one character left, and that's gonna be the length for the string, because we only have one particular character left, and that's gonna be the length of the palindromic string. Okay, that's the base case, and let's go over the example we have. So ABBBA, so ABBAC, and these two are not the same. These two are not the same, so we are gonna go over here. So in here, just like before we described, we're gonna sacrifice one character. We know A and C are not matching, so we either sacrifice A, it become BBAC. We sacrifice C, and J will be shrink to the left, and that's how the recursive function works right here. Or we can have I plus 1. I is right here, plus 1. Oh, I'm sorry, I plus 1 is actually this, and J minus 1 will be here. ABBA. So we will sacrifice this guy actually. So I and J is here. So we can either move J, we can sacrifice this A, it become BBAC, or we can sacrifice C, it become AABA. So AABA will be in this recursive function, and the recursive function will come back, and I and J already being moved. The I is right here and J is right here. And when we going through the recursive function, we know the I and J, SI and SJ, under these two index, the character are identical, and we're gonna plus 2 because we find a match, and we are shrink on both sides, and we have BB left. And when BB going into recursive function, we already have 2, and the next layer will find, oh, we have a match again. So once we have the match again, so I will become here, I will go over to here, and J will go over to here, and they are already crossed. So J already greater than I already greater than J, so we return 0, but we already have 4 stored in the stack. So when the second step being called back and called back all due to the main function, we do have a match, which is 4. So in this case, the longest palindromic subsequence is gonna be 4. You know what? The order for my slide might not be right. Let's go over the next problem. Let's go over this guy. Yeah, this guy will be, this guy is supposed to be the next one. Longest palindromic subsequence number 2. So a subsequence of string is considered a good palindromic subsequence if it is a subsequence of S. It is a palindrome, has the same value if reversed. So everything in the first two conditions are the same. So with the previous problem, we don't care about that. And so here's another condition. It has to be an even length. So this is the first caveat. It has to be even length. And the second caveat is no two consecutive characters are equal except the two middle ones. Except the two in the middle ones. Let's check some examples we are given in the examples, right? So in this case, they are picking a BBAA. So no two consecutive characters are equal. B and A cannot be equal, except when they meet in the middle. A and A could be identical. C and C could be identical. C and D cannot be equal. We can have C right here. We can have CDC, CDC, and we cannot have CCD, 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 DCC. That doesn't work. We cannot have CC on the left or on the right. That doesn't work. We cannot have two consecutive characters are equal. If we remove the last two conditions, that will be just like the problem we just talked about. But now we have another condition. And when you use trying to solve this particular problem, and now you need to memorize, you need to find out what is the previous character we pick in the last layer. In order to find out what's the previous character you pick from last layer, if you solve this problem by using bottom up, you'll need a 3-dimensional array to cache the value. And that's why I recommend to use top down. And we don't care because all we need to do is to add another parameter into the recursive function. But when you're trying to solve like with the bottom up, you need to deal with a lot of like special cases and initialization. You have to think about how we cache that, and which is very troublesome for beginners. So when you use top down, it's as simple as that. So I didn't manually cache that, but you could translate the code. Okay, so how do we do this? We are starting with left, which is I, and right is J. So these are still the index like we are passing for the very beginning and the very end. Okay, and we are passing a random character. It doesn't matter what character like you're passing. So as long as it's not the lowercase is English letter that giving the question, so you can pick any character as an initialization. So we need that because we want to track what are the previous characters we pick in the last layer. How do we do that? So we are going to the function left, right, and previous character. So now this is a random character. We haven't assigned anything yet, and this is the base case. When i's go over the j, we return 0, just like before. And we have i's right here and j is right here, and I and j are not the equal. So that's why we either pick I plus 1 to j, which is BBBAC, or I j minus 1, which is ABBBA. So we just check ABBBA. Okay, ABBBA comes over here, and now we just ignore C. So we don't care about C anymore. So in this case, the pre haven't changed yet because we haven't find a solution yet. We haven't find anything that are two character match. So let's still keep the random character as our pre. And we have ABBBA. A and A are matched right now. A and B are matched right now. And SI, which is A, is not equal to the random character. When they are not equal, so we can go ahead and check. Perfect. So we have this guy. Okay, we have this guy, and I will up to here now because I was previously here, J was previously here. Now I plus 1, J plus 1, they both are B. Perfect. And before we go over to the next layer, we will assign the pre as SI because when we go into the next layer, BBB, we don't want this guy to be A. So that's why we will assign pre as A. Now we go into the next layer. We go into next layer, I and J will be here and here. And we check B and B are equal. Perfect. So B and B are equal. And we go over this, and I plus 1, J minus 1, they are identical right now. Okay, so this is how the base case deal with the third condition. In the previous one, we have I is greater than J. We return 0. When I equal to J, so we return 1. But we don't want that anymore. So when I equal to J, if they are equal, we return 0 because we don't have even number of length. So when we have a single number in the middle, we don't want that anymore. So that's how we cache that, the third condition in the base case. So this pre is the core idea of how we solve this problem. Okay, so now we already go over this problem. So let's come back to other problems. Okay, now we're gonna find the minimum cost tree from the leaf values. So given an array ARR of the positive integers, consider all the binary trees such that each node has either 0 or 2 children, and the values of the array corresponding to the values of each leaf in the in-order traverse of the tree, and the value of each non-leaf node is equal to the products of the largest leaf value in the left and right subtree respectively. Among all the possible binary trees considered, return the smallest possible sum of the values of the non-leaf node, and it is guaranteed that this sum fits into 32 bits. Okay, this is for Java and C++ developers, so they don't want to overflow for the integers. Okay, we are given this array, and this array represents the leaf of an in-order traversal tree. So that means like it's going from all it's saying is going from left to right. So these leaves are going from left to right. So you are building up a tree by using the leaf node. How do we building up? It's by using the left hand. So when you splitting from the middle, you are taking the maximum value from the left, and you are taking the maximum value from the right, and you multiply them. So for example, that in this case, for example, right here, we want to separate the 4. So we just want to ignore the 4. We are not even in the same family. So we want 6 and 2 become a family tree. So 6 will pick the largest value from all its subtree. But in this is a really bad example because 6 does not has a subtree. So 6 does not has a subtree. It only has itself. That's why the parent for 6 and 2 will become 12 because we only have 6 right here. I have 2 right here. For example, that if 6 already built a tree, we have 8 right here, we have 10 right here. It wouldn't happen because 6 should be the parents. But just for example, right, we have 8 right here, we have 10 right here. And this 12 should not be 12. It should be 12 times 2, which is 24. Because we are picking the largest number from the left-hand side, and we are picking the largest number from the right-hand side tree. And then we're building up this. So the problem looks confusing, but when we actually trying to break them down, it's actually easy. So all we need to do is just like the burst balloon, we are bursting each of them. So we're picking every one of them as a parent node. And then we are just keep going over. So how do we do that? So we still have the left and right, and we're still breaking down from our left and right. And just in the middle has something different, right? The middle we have, so for example right here, so let's say we have 6, 2, 4. So we are picking 2 first. We are picking the, oops. Okay, we are picking 2 first. So we are picking like somewhere in the middle. And we want to merge this 6 and 2 first. So how do we merge these 2 guys? It's by picking the maximum number from I to k from the right hand side, which is k to j plus 1. So we're picking the maximum number right here, minimum number right here, and we merge a tree, which is 12. So that's how we build the tree value. So once we have the tree value, we already merged that guy. We just ignore that guy. K is being picked. So we're going to have I all the way to k, and they're going to form a tree. And the right hand side, we're going to have k plus 1 to j, and they're going to form a tree. And our tree node is right here. That's how we do it. So, and if you look at the code, there actually some optimization we can make because we are searching in the range and trying to find the maximum value, and we're trying to search in the range to find the maximum value. So we can do some pre-processing right here, and we either loop from the left to right to find the maximum values along the way, and right to left and find the maximum along the way, and to optimize this to 01. Otherwise, this is going to be n to the cube, which is not really good. So I'll do some optimization later on, but I haven't done yet. So you can go ahead and do some optimization right here. And that's for this problem. And next one is a little bit different style for interval dynamic programming. String printer. So there's a string printer with the following 2 special requirements. And the printer can only print a sequence of the same character each time. At each turn, the printer can print only new character from the starting and the ending at any places. We'll cover the original existing character and given a string consisting lower English letters only, and your job is to count the minimum number of the turns and the printer needed in order to print it. So basically what the question is saying, you have a string printer, so each time you can print only one character, but you can one type of character, but you can print infinite number of the characters. So in this case, like how many character we're gonna print, how many times we're gonna print. So actually twice. So you can either print A, B, B, B. But that's actually not the optimal solution. So the optimal solution we will do is I'm gonna print A, 6A, and I'm gonna print B, B, B to override the last three characters. Why do we do that? That's actually the next example. So we have A, B. In this case, we are seeing A, so we are not just print that particular 1A. We're gonna print 3A, and then we're gonna print B to override the second one. The reason is that if we are print A for all of them, we are hoping that in later time there possibly be another A right here that we don't need to override. Finger crossed that we're gonna cover as much A as possible, and maybe like for example this is A, B, 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 A. Oh wow! So we are expecting to override. Expecting to print this 3A, but when we print A for all of the characters and we have A was being printed, that's perfect. So we covered this guy. And we saved the one step. So otherwise we will print A, B, 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 A. Okay, that's 3. That's not good. Actually, the optimal solution will be 2 because in the first print, we cover all the string to do that. Okay, so given this hints, so we can go ahead and solve the issue. So how do we do this? The way we do this is a slightly different. So we can initialize the result with the worst case. So what is the worst case to print all the character in a string? It's actually the length of the string. The worst case is gonna be we have 6 characters. It's gonna be A, B, C, D, E, F. That's the worst case. We're gonna print this 6 times, and that's gonna be the worst case. And once we initialize the worst case, now let's move on to find if there's any optimization we can make. Yes, of course. So this is not A, B, C, D, E, F. We initialize the worst results as 6, but actually when I print 8 all the way down, we're gonna resolve these 2 guys, right? But how do we reflect this into the code? How do we do that is by we still have a k looping through I and j. We treat this as an interval, and k will compare with the first elements. For example, k can be here, could be here, but when k up to here, when we compare it with the first guy, we realize, oh wait a minute, so this guy and this guy are identical. So which means if I print this guy all the way to here, this guy can save my life. Perfect. So this guy life can be saved by the first print. So we can eliminate this guy because we know that this guy can be saved by this. So now let's just do a recursive call right here. Just check the first 2A, hoping there's another magic to happen. And BBB itself can be another recursive function. So BBB will go into recursive function and restart from 0, and this is I, this is J, and B and B we pick a K right here, and they find, oh, this guy can be saved by this B, and we're going into the recursive function. And let's go over some concrete code first. So just like we talked about before, we have a memo, we have a left and right and J and memo, and we calculate memo, everything standard. And the base case when Ji is over J, so forget about it, we don't have character left, so we just return 0. And this is actually the initialization for the worst case. So why is that? So I initialize was right here under A, and J is right here, and I will increment, and the stack will +1, and I will increment again, stack will +1 again, I will increment again, stack over +1 again, and I will overflow, and then we are gonna have 4 as total assigned to the result. So this is the cases we calculate the worst case. We are treating, it doesn't matter when I increment, we're not comparing anything. we are not comparing with anyone. We just increment the value to increment 1 to the value. We treat all the characters are distinct. They are all distinct. So that's why we have the worst case right here assigned as result. And we are looping through from I plus 1 all the way to j. All the way to j. J plus 1 is not inclusive, it's exclusive. So that's why we are going all the way to j. We are comparing each character to a. And just like what we described before, if k is equal to I, so now like we're breaking right here, right? So we have I is right here, and k could be here, could be here, could be here. So this is the best cases, right? When k is up to here, we find k is equal to I, and we're gonna recursively calling I all the way to k minus 1, I all the way to k minus 1, and k plus 1 all the way to j. They're the same thing. So only have b left. So b can be a single one, hit the base case, and you know b can a single cases, right? And a, this two will return two, and eventually we're gonna these two will return 1, right? So that's how we solve it. That's how we solve it. So we pick a number k comparing with the first one, and hoping that these two are same. If these are same, so we can recursively solving the previous one, and this can also be saved, and that's why this will return 1. Okay, so why do we initialize this guy as the worst cases? So why do we do that? Why not just doing this as a infinite number? And the reason is that if all of the characters are distinct, A, B, C, D, we will never find a k equal to I. None of them are. A, B, C, D will never be equal. We will never even going into the recursive function, and the result will be infinite. So that's why we will initialize this as a worst case, and hoping that we can pick a k, can optimize that. That's how we solve it. Okay, so let's try to solve another really hard one. So given an integer array ARR, so in one move, you can select a palindromic subarray I all the way to j, where I is less or equal to j, and remove that subarray from the given array. And note that after you removing a subarray, and the elements on the left and on the right of that subarray move to fill the gap left by the removal. So return the minimum number of the moving needed, remove needed to remove all the numbers from the array. So let's check one of the example first, right? So you have 1 and 2. So each time you want to remove a subarray, which is palindrome, and we don't have palindrome except the individual item. So 1 and 2. So the worst case is going to be 2, and the minimum number you can remove is also 2. And in this case, you can pick 1, 3, 1. You can go ahead with the 4 first. So because we need a subarray, and once you remove 4, and the rest of the number will be merged like burst balloon. So 1, 3, 1 will be merged as adjacency, and 1, 3, 1 you can move next, and you're left with 5. So this is the third time. So how do you solve this? This is actually very similar to the printer, strange printer. So if you think about it, every time we need to find a worst case. So what is the worst case in this case? And the worst case is every single number in this nums cannot be formed as a palindrome. So if there's no palindromic array within this array, so the worst case will be every time we will remove 1, 1, 1, 1, 1. So every time we will remove one of them. So in that case, we're going to remove all of them. Each time we remove 1. Okay, so that's going to be 5. And with the worst case in mind, and let's think about how we solved strange printer. We pick a number that is identical. So we compare with the index I. So if they are the same, that means we can skip one step, because when we remove 1, we can remove this 1 as well. So that's how we translate this into string pointer. I think the problem is almost identical. So we want to find this particular number that is identical to this guy, and they can be print together. They can be removed together because this is palindrome. So once we remove these two guys, and you are left with this two, so we can recursively solving this. And solving what? Solving from I to k minus 1. Why is that? Because we are hoping. Oh, now in this case, it's actually I plus 1 to k minus 1 because we already removed this guy, we already removed this guy, and we want to try to solve these two together, 3 and 4. If there's something in the middle, that's okay. But we want to solve the boundary together. Can we remove 3 and 4 together? Right, so that's the thing we're trying to optimize. So still, like just the string pointer, we wanna get the worst case first. So the worst case will be increment I. So 1, 2, 3, 4. I will be increment all the way to over j, and we return 0 from here. But each time in the recursive function, we'll plus 1. So in this case, the worst case will be 4, and that's what is being assigned as the result. And we are hoping somewhere we can find a k. So start from right here. I is right here. J, we start from I plus 1 all the way to j. We are hoping there will be one character, one number will be identical to this guy. We could find it, which is this guy. So if they are equal, we are recursively solving something in the middle. But in the middle, we do not have anything. So forget about it. So we return 0 from here, and this guy will be removed together. And we are left with the 2 and 3. 2 and 3 are identical. So 2 and 3 will also go back to the recursive function because that's on the right hand side, right? We are removing this guy, and now k plus 1 is right here and j is right here. This is interesting. So we are going to 2 and 3, and I is right here and j is right here. And how do you solve this? This was being initialized as 2 because I will be here and increment, and the worst case will be 2. And we would never find a number because we only have 2. We will never find a character k will be identical to this guy. So we will never even go into the if condition, and we will return 2 from here. So 2 plus 1 will be 3, and that's how we return 3 from this case, and that's how we solve this problem. So let's go over the next one. So minimum cost to cut a stick. So we're given a stick, and so each time we can cut. So we're given a cut array. So each time we can cut at somewhere, and each cut will cost the length of the stick. Will cost the length of the stick. So let's read the question just in case you never read it. So given a wooden stick of length n units, the stick is labeled from 0 to n. For example, a stick length 6 is labeled as follows: 0, 1, 2, 3, 4, 5, 6. And given an integer array cut where the cuts I denoted a position that you perform a cut at. So we will see the cut in the next slide. You should perform the cuts in order. You can change the order of the cuts as you wish, and the cost of every cut is the length of the stick to be cut, and the total cost will be the summation of the costs of all the cuts. And when you cut a stick, you will be split into small. The wood will be splitted into 2 smaller sticks, and the sum of their length is the length of the stick before the cut. Please refer the first example. If you read this question, so my understanding is this is identical to burst balloon with one caveat. So burst balloon, the value you will get is by multiplying the neighbors and blah blah blah. And now this case we don't have the we are looking for the minimum one. So that's the first thing. And the second thing is we are looking for the value. So the recursive value we are changing is not the products of the neighbors with that particular value anymore. The value we are seeking is the cuts, which is the length of the wood. Okay, perfect. So with these two caveats in mind, let's check the example. So we are given a wood, and this wooden stick has several positions we can perform a cut. Let's say we cut at 3 first. If we cut right here, and the cost will be 7 because we are using the last position of the cut minus the initial position. Start from here, you'll realize, wait a minute, how do you do that? It looks complex. It is complex only in the first cut because we do not have 0 and 7. So that's why, just like the burst balloon, we need a virtual boundary. It's just 0 right here, 7 right here. So we can perform the cut by using the last number 7 minus the first number 0. And then we can get 7 as our cost. So that's our first cost. And the second one, from this wooden stick, so we can perform a cut right here. And we can split into 2 different sticks. And the total length will be 7 minus 3. And that will be 4. That's the second cost. And the third one we're going to cut from... oh, here, I'm sorry. So we cut right here. So it's 3 minus 0. So 3. Because the length of the wind stick is 3. And same thing right here is 2. So that's how we perform the cut. And that's how we collect the cost. So the cost will be easy to calculate. It's going to be the boundary subtraction. Except the first cut, we do not have the boundary. And we need to add a virtual boundary. And that's how we solve it. So we sort the cut. We need to sort the cuts in order to solve. Otherwise, when you have, for example, a 3, 5, 1, 4, geez, like you cannot have 4 minus 3 as the total. So if that's the position you want to perform a cut, right? So you need to sort, and you need to add virtual boundaries. You need a memo. You need to go from I to J. Everything's standard right here. I'm not gonna beat that horse. And when we have only 1 unit left, we cannot perform a cut. That's the smallest unit. So forget about it. We return 0, and we want to find the minimum value, and then we return. We initialize as the maximum number. Okay, so we can perform a cut from I plus 1 to J. We can perform a cut from I plus 1 to J. And every time you perform a cut, what's the cost? The cost will be the length of the stick. So which is cost J minus cost I. Okay, perfect. So we got the cost. And we can break down the wooden stick into 2 parts. The left part and right part. Just like the burst balloon. And we're going to find the minimum value. And then we got it. That's how we solve this. And we already go over this problem. So I think we are finished. And we have completed 9 problems for interval type of dynamic programming. I think it's a big achievement. If you understand all the problems right here, I think you already got a core idea. And in the future, so if you see the similar patterns, you will solve it. And if you like my video, please subscribe to my channel, and I'll see you in the next video.